Okay, go for it.
Okay, thank you very much for the introduction and for the invitation. It's a pleasure to be here. I'm still excited to learn about neutron stars, which I feel like I know nothing about. So I'll try to focus on some universal properties of superfluid turbulence that perhaps with some modifications could be relevant to neutron stars. And I'll also focus on zero temperature, which is perhaps the most non-trivial regime of superfluid turbulence decay. And generally we know, I think it has been mentioned a few times, that we have generally two types of tangles in superfluids. Non-structured tangles, which is those that typically arise by, for instance, Kibble-Zurich mechanism, where there's no order in vortex lines, and tangles which behave generally classically at large scales, which typically are obtained by classical means, such as steering, for instance. But they behave somewhat differently. We'll discuss in some detail what the differences are. But I'd like to set the stage for the theory here. So first of all, there's generally two scales that we need to focus on: the system size scale, where the energy is typically pumped into the system, and it is usually, at least in helium experiments, it's much larger than the healing length, the vortex core. It's actually 15, the log of the ratio is typically 10 to 15 in helium experiments. So it tells you that hydrodynamics is a very good description of the problem. So you can neglect all the microscopic physics when you study how the energy is dissipated in the system. And then if you look more specifically at the dynamical setup, well, you see that the energy is mainly concentrated at this main scale, at the biggest scale in the system. And there's actually no dissipation mechanism down to very, very low scales. We'll see what those scales are, but you can imagine that if the energy reaches the scale of the vortex core side, then of course there will be some dissipation mechanism where the hydrodynamics breaks down, but we'll see that in fact they're quite efficient mechanisms even in the hydrodynamic regime, well in the hydrodynamic regime, such as sound radiation. Another property is that kinetic times in the system, that is, the typical times at each particular scale that takes to process energy and bring it to an adjacent scale, they increase progressively with the wave number. So kinetics becomes progressively faster as we're going down the length scales, and that essentially leads to.
But this is not the opposite of what you just said. You said that with increasing K, the time scale is faster, so the time is smaller, right?
Right. Thank you. So kinetic rates get progressively right. So kinetic times get progressively shorter with wave number.
Okay.
Right. So I was thinking in terms of rates, and that's the usual thing to mess up. Right. Thank you. Okay. So and under these conditions, it's standard that the relaxation takes the form of an energy cascade. That is a regime where energy which is generated at this main scale, at the biggest scale, gets transferred through the length scales down to shorter and shorter length scales, but in a very specific way. That is, the regime sets the decay regime is quasi-stationary. That is, it is controlled by the slowest length scales, which are the time scales, which are time scales at the biggest length scale, and then at all shorter length scales, kinetics adjusts to the energy flux that is sent into the system at the larger scales, and transfers it through the energy space as a constant. So it doesn't change, constant in the sense that it's uniform in the wave number space. So it doesn't change with across the length scales. So that's the essence of the stationary.
Kinetics, are you talking about the kinetics of the superfluid solvent?
No, there's no phonos yet. So it's just a superfluid vortex that we're talking about. So the kinetics of vortices.
Okay, but if they bend and do something, they might generate phonos too, right?
Right. Okay. So that's my next slide. So I'd like to focus on mainly on two interesting readings. First of all, in both of these pictures, when you zoom in sufficiently to length scales where you can distinguish individual vortex lines, you'll realize that the energy has to be transferred by waves on vortex lines, the so-called Kelvin waves, down to shorter length scales. Right, so this is the universal part of the decay scenario in both non-structured and quasi-classical tangles. And eventually, indeed, as the length scales get smaller and dynamics of Kelvin waves becomes faster, then the radiation of sound by Kelvin waves becomes efficient. Right? Obviously, at large scales, when dynamics is really slow, then you don't expect much of sound radiation, but eventually you can reach the scales, and we'll see that actually those scales are still much larger than the healing length. So you're still in the dynamic regime, you can efficiently dissipate all the energy into the sound. Okay, so that's the general picture of decay. Now, if we want to build a theory, we need to write down some equations. So the and by the way, I haven't emphasized this enough, but we're working at t=0, meaning that there's no normal component, obviously, and that's why I focus on sound radiation as the main dissipation mechanism. But you can imagine that if there's some non-zero temperature, still low, but non-zero temperature in the system, the dissipation between mutual friction will compete with sound radiation in terms of efficiency of energy dissipation, and you can think of mutual friction to be the main cutoff mechanism of the temperatures is sufficiently high. Okay, so, but in the high dynamic regime, the main equation of motion that describes the system is the Biot-Savart equation, which immediately follows from Kelvin's circulation theorem, where the vortex lines are described by geometrical lines, right? So the thickness is zero, and the motion of a point on the vortex line is given when the velocity of the point on the vortex line is given by an integral over all vortex lines. So in principle, it's a non-local equation, and it conserves these two integrals, which up to dimensional constants are just the energy and momentum, but have very specific meaning in case at least when the vortex lines are singular, when you can neglect singular, well, they're alone, you can neglect coupling to nearest neighbors, then the energy is approximately the total line length, and you see by the meaning of the integral, so it's just the area of vortex loops. So that helps to think a little bit when you try to figure what the dynamics is, these diametrical terms. Now, the first approximation to dynamics, which actually is a local equation, by this large parameter, which is the logarithm of the typical curvature radius of the vortex line to the healing length, which at least in helium is quite large. You can neglect all the non-local contributions and just focus on the logarithmically divergent part of this integral and arrive at the so-called local induction approximation. But this model is it's relatively easy to solve, and it does give you certain description, but you need to be very careful because it is well known that this is an infinite integrable model, so it has an infinite number of constants of motion in addition to these two. And so it doesn't allow any pure kinetics. It doesn't allow nonlinear interactions between waves in a way that transfers energy between different modes. Okay, it doesn't lead to any kinetics. So if you want to describe pure kinetics, and by pure I mean without reconnections. So as we'll see, reconnections play an important role, but eventually they cease at short enough length scales, they disappear, and And one has to think of the purely nonlinear cascade, and that can only be done in terms of the full.
Can I ask you about algebra here? The energy there is the integral of the volume.
No, it's the line. It's the cross. Oh, it's ds. Oh, okay. So this
It's
ds. Sloppy. It's ds 0. Yes, yes. So it's a double integral. Yeah. Apologies for this bug.
So it's a linear integral.
It's a line integral, double line integral. Yeah, it's the same as
What is double line?
ds not.
Yeah, ds and ds naught. So these, both of these are
But what's S naught and what's S?
Yeah, right. So let me explain this. Sorry, wait. Yeah, sorry for being sloppy. ds s naught divided by s minus s naught. Right, so it's a double line integral, which you take over all vortex lines.
Over, I'm sorry?
All the vortex lines that you have in the system. Right? So if your vortex lines are separated far enough, then you can see by the denominator, the integral reduces the integral over the
S and S naught run over one vortex line, S naught over the other, right? And you take all the pairs.
Right, all possible pairs. Yeah, it can run over the same vortex line as well. So ds and ds0 can run over the same vortex line as well. So they run. So imagine you have a parameterization of the whole tangle, some unique parameterization where each point is parameterized by a parameter, and basically you have to integrate over this parameter with two line elements running independently.
You don't need the 1/2 in front.
Okay, there's density, there's circulation quantum, and all sorts of things if you want to get energy, but of course, for theory, you don't care about dimensional things, even pies.
You don't care about numbers.
No, seriously, you can look it up. It's steady if you want. Right?
This one using the self interaction does not play any role.
Oh, it does enter there. So again, this integral will reduce to a logarithm times the line length, essentially close to the vortex line. If you can neglect coupling between different vortex lines, if they're far enough apart, then the main contribution will be the same as that in the local induction approximation. That is from the denominator in this integral, which diverges at 0 and is regularized by the vortex corsine. Okay. Right, so I can go back to.
And for the P, the area goes. How is that?
It's a vector quantity, so it's a vector product, cross product.
You integrate over the vortex line.
Yes.
So it's a line integral.
So it's a line integral. Well, this is also a line double line integral, but this one is basically this S and ds runs along the vortex, so we have to take dot product, so point that way or that way, and integrate it over all vortex lines to get the total sort of area, algebraic area, if you will, because some of them will be positive, some of them will be negative. You add them up, and you'll get the vector. Okay.
So now, if the total line vortex is not conserved, you, for example, if you run a simulation of the CNR, you'll be outside of this regime because something will happen. So what typically will happen if that's the case?
If you have many vortices in the system, you can transfer the energy into the interaction between different vortices. So if you have just one vortex line, then indeed it's approximately the vortex line length. There's still some corrections, but up to this logarithm controls these corrections. They're going to be small in this logarithm. You'll see that you have to conserve with logarithmic accuracy. You'll have to preserve energy. But if you have many vortex lines and they're allowed to interact with each other, then of course, your length as vortices approach each other, you can increase the length or decrease. You lose the energy. You have to decrease the length. Okay.
Oh, so this is the dilute line density, something like that. You have.
Well, this is exact. So this is exact, and this is just to get some intuition in the case when it's dilute. Yes. So you see, I read approximately, but don't confuse. I mean, this is an exact expression. This is an exact integral of motion.
Okay.
Right. With the regularization.
With the regularization, that is usually assumed like this. Yeah.
Okay.
Thank you. Question.
Yeah.
You have a vortex angle.
What's the spectrum of its excitation? Looks like you can have Kelvin waves, you can have oscillations of some kind of amplitude lattices there. What do people
Right,
know
this
the
is-
spectrum is?
This is a very good question because it becomes very confusing at times because people try to treat the Kelvin wave spectrum, for instance, with the energy of fluid volume, the kinetic energy spectrum on equal footing. It's not, they have different physical sort of nature. So indeed, at large scales, the relevant description would be in terms of the kinetic energy spectrum, just like in the form of war of classical turbulence. And there you would look at energy per unit volume, for instance. But if
What does it actually, do people know what it looks like? If I have a vortex angle of some size L, what are the modes of that?
You want the small amplitude?
well, it behaves just classically. But I'll mention this. Okay, we'll get to that.
But then there are the Kelvin mode has this definite.
So the Kelvin mode is it requires a different description because it becomes relevant when you neglect when the interactions between vortices are relevant, when the coupling between different vortices are relevant, and you're looking at singular vortices. And then, of course, in a single vortex, it makes no sense to define the energy spectrum of the kinetic energy because it's mostly given by the circulation around the vortex. What we actually need to look at is the deformation of the vortex and the energy associated with this deformation. And that's why we describe the Kelvin wave turbulence in terms of occupation numbers or amplitudes of waves on vortices as a function of wave height.
Another question is concerning the next slide.
Yeah.
You say the system is integrable,
Right.
but if you have many vortices that they float around, you see they might cross once in a while.
Right. Exactly. This is a
So
very
you're
good
still
point.
incredible in that.
This is a very good point. I was going to mention it on the next slide. So indeed, and I will, but yeah, probably there's going to be too much information. So I'll say it now. So indeed, the reconnections, they effectively lift the integrability constraint. You can see that they break the integrals. They make some of those integrals divergent in the conservation laws, and they therefore reconnections, with the help of reconnections, you can have kinetics, no trivial kinetics in the local induction approximation.
So you have integrable motion until you come to
Until you cross.
and then after the next connection.
Exactly. And this is part of this scenario. So I just wanted to flash a quick slide of.
Yeah, but now
Yeah.
you might have a problem. You might have a reconnection in this end of the room and another reconnection in that end of the room. How you are going to treat this situation?
They correspond to different length scales, but let's discuss that on the next slide. So I just wanted to say that I'd like to focus now on non-structured tangles, and this is a typical example. It's a simulation, but I think there are experiments now being pulled out of it as well, which demonstrate that as the system equilibrates, you need to start with high thermal state, and the system equilibrates and reaches the Bose-Einstein condensate. In its final state, you end up with a random vortex tangle. These black lines basically are the vortex lines. So it's quite a standard, typical situation in non-equilibrium Bose-Einstein condensation. Now, it is somewhat simpler decay scenario than in the quasi-classical tangles, but it has some general features that will be common. So we'll start with this. So this is an overview of how, in this case, the tangle decays. So this is the Kelvin wave. And again, there's no structure of vortex tangles at large length scale, so it makes no sense to speak about the kinetic energy spectrum in this case. We describe the system purely in terms of Kelvin wave amplitude in wave number versus wave number scales.
What's the meaning?
Right, so the BK is the amplitude of Kelvin wave with a wave number K. It's just the geometrical amplitude, and K obviously is the wave number. So what happens is that at the largest scale, at the scale of typical interline separation, when the vortex lines cross, their crossing leads to generation of Kelvin waves with wavelengths somewhat shorter than the typical scale at which the vortex lines cross. So this problem can be solved separately. There's an exact solution, in fact, because with local induction, up to the local induction approximation with this large logarithm, you can write down an exact solution that actually demonstrates how the Kelvin waves emerge in the reconnection. And so then at the smaller scales, the Kelvin waves cannot decay to even shorter length scales, so they accumulate there, okay, due to reconnections. The amplitudes of them will keep growing until the vortex line can self-cross. Okay, when the vortex line self-crosses, then it generates a vortex ring on one end. On the other hand, the Kelvin waves of even smaller wavelength are introduced into the system, and both on the rings. And this is the mechanism that supports the cascade in presumably a certain inertial range. Okay, so yeah.
In those processes, how do the quantities during this reconnection, does anything change? You know, the energy and the P, they're still conserved, right?
Yeah, everything should be conserved up to some small effects which are negligible in the hydrodynamic limit, such as, for instance, emission of phonons or rotons, presumably, from the volume of the reconnection, which is obviously has the scaling with the healing length, which drops out of the problem completely, and at this length scales. And then the vortex rings that appear, they don't play any special role. They just get reabsorbed by turbulence via reconnections as well. So they just contribute just the same way as the decay of the vortex angle that is created in the reconnection process. They contribute to the kinetics.
How long do they survive the rings?
Well, until they cross with the nearest vortex line. So you can estimate, you know, given the size of the ring, typical length scales, you're looking at what the cross section of you know, the velocity of the ring, obviously, from which you can estimate how long they need. But they will eventually be absorbed by the bulk turbulence. If you neglect surface effects, which will obviously lead to emission of vortex rings outside, then whatever happens in the bulk essentially absorbs the rings anyway. So
I'm a bit confused. How do you define the Kelvin wave amplitude? Because usually Kelvin waves are just a small displacement from the equilibrium configuration of the straight. So here I see like a vortex that makes a ring, and this is not, of course, a small deviation from the straight configuration.
Well, okay. So if you want to be mathematically precise, you can of course introduce a Fourier transform. We'll do that. But I can give you a heads up. So you just Fourier transform the vortex line and decompose it into occupation numbers, if you will, and then the occupation numbers essentially give you the spectrum, which you can translate back to the amplitude. So the amplitude is just some integral of wave packet of occupation numbers over a certain range of momentum, which are order of the momentum or wave number you're looking at. We'll look into that. Okay, so this process continues. So it is supported purely by reconnections, and in fact, by the way, quite interestingly, you can ask
what about the process you have out there, which is the pure connection?
Yeah.
So where that comes?
Oh, it's just the tangle itself, which is, you know, this random tangle.
But do you call it self-crossing?
No, it's not a self-crossing. It's a crossing between two separate lines.
So
right.
What way is that valid? You seem to have only one.
So this happens at different length scales. You can imagine in the theoretical limit, you know, these length scales could be order of magnitude different. So this self-crossing happens somewhere here if you zoom in. Right?
But of course, if you those might be the same vortex in the top.
Yeah, of course, it's the same. It's the same. It's probably this vortex which has grown amplitude high enough so that self-cross, but it's tiny on this scale. Right?
I mean, like your vortex could have a bit, in the top left corner could have a big loop.
Yeah, of course. Yeah.
So they're the same sort of thing, scale.
A different length scale. It's the same vortex. Yeah.
And the law, it will be B proportional to K to -1 everywhere the same in that region.
Yeah. So in this region, you can actually work out what the spectrum is, and indeed it's just a quarter of the length scale of wavelength.
Okay.
Right. So it's the amplitude of wavelength, because essentially it's necessary to maintain this self-crossing process, because the self-crossing is a probabilistic effect, and you need to have high enough amplitude for the Kelvin wave to loop on itself. So if the amplitude was lower than this, then the process would be exponentially suppressed. It would be very weak, and this is what happens eventually. By the way, I should say that strictly speaking, there's a logarithmic correction, so the spectrum does go down. You have to include the logarithmic correction to account for the constant energy flux. The energy flux has to be constant in this quasi-stationary regime. So you have to include logarithmic correction. So eventually the amplitude does go down, and the purely non-local interaction of Kelvin waves without reconnections take over the cascade. So they become efficient enough, the length scales are short enough so that kinetic times are fast enough at this time, and the purely non-local interaction between Kelvin waves take over the cascade, and that changes the spectrum. It quite naturally becomes slightly steeper. Okay, and eventually, and that goes on until eventually the cascade is topped out by sound radiation, and all the energy is eventually in decays in the sound.
Another question. In this region, you say that everything is captured by local induction approximation.
Well, here, so up to here, it's all captured by local induction approximation. So
They,
with corrections which are small.
you run this integrable system, and then you have a reconnection,
Right.
and nothing happens there. You conserve the energy, whatever.
Right.
percentage change.
Up to this large logarithm, you conserve the energy with 10% accuracy, you conserve energy. And so this becomes the leading mechanism. But then eventually the local processes become important because their kinetic times go faster.
So you don't lose energy at all in that area due to phonos or anything else.
Oh no, this is very weak. So you do have to go to considerably smaller scale. So this happens at the length scale of, I don't know, 1 centimeter. And
You have, but it's weak.
yeah, of course it's always there.
So like the process of a vortex ring, which eventually will close in on itself and annihilate, that's all phonon emission, and it's very inefficient at long wavelengths, but at short wavelengths.
Right. Yeah. Yeah. It's a we'll see. It's a quadrupole radiation. It's a high power.
So what happens below? So R0 is your volume
Essentially. Yeah.
essentially. But I mean, you can send your R0 to basically infinity, and I mean we're
Theoretically, yeah. That's what we do. That's what we do.
So exactly. But you have written that basically the LIA is most of this power law k to the -1, while this this crossing of those is a small thing. But what happens below are so basically when you send R0 to infinity, is everything there is just a pure k to the -1 power law to k equals 0, and is the physics also governed by those crossings of vortices, or
Well,
is something else happening there?
I mean, this limit, viewed this way, this limit makes very little sense because everything is controlled by this logarithm. So if you set this logarithm to infinity, you'll just get only this part of the spectrum, and everything. Local induction approximation becomes essentially exactly this limit, and then you forget about everything else, and that just keeps going.
So this is your finite size, basically having those.
Right. Well, yeah, but I mean, I don't think it's a good idea to think in terms of thermodynamic limit this way.
But you're pumping energy into that scale.
You're pumping. This is the energy pumping scale, right? So it does enter in any turbulent problem. It does enter non-trivially, right? So
If you have a mesh that's
you
doing
cannot
this,
extrapolate it out.
then that's the scale of.
So you can think of thermodynamic limit as increasing the system size, but keeping the energy pumping scale fixed.
Right. I didn't realize this is your energy.
Essentially, yeah. I mean, they typically are the same order, but.
Sorry, just other related properties, like for example, double reconnections are more complicated. They all follow this one over K.
Well, double, because it's all probabilistic. Double reconnections would be extremely rare, and irrelevance just
They would fall within that.
Yes. Well, I'm not sure if anybody has looked at that explicitly, but they would be statistically unimportant because of the small phase volume that.
What exactly is a double reconnection?
Well,
You mean two vortex rings, not one between.
yeah, two votes. They don't just sort of collide and have a result, but they sort of collide.
But is it not just two of those with close?
In fact, there's a well-known.
It is effectively to them close proximity, but I don't know if you can isolate them as two separated.
There's a very, very well-known problem when two vortices reconnect, which have a very small angle between them. I don't remember what it is, like 0.1 or something like this, and that creates a cascade of vortex rings instead of just two vortex angles that just breaks down into vortex rings. But again, this angle is, I don't remember exactly, but it's something like 0.1. So
basically the speed at which that goes becomes so fast that it doesn't have.
yeah. So they when this vortex angle becomes starts unfolding, it basically unfolds out of the plane and in plane, and it just kind of wraps on itself and cuts itself up. That's essentially what happens.
But energetically, that's probably a hard thing to do.
I mean,
So
it's
it
a
doesn't
conservative
have to-
process, so
Oh,
it's just that statistically it has a very small phase space. It's not very relevant statistically. It's 10%.
yeah, because that's a vortex anti-vortex.
Yeah, that's also important. That's also important. Yeah. So
But that would be likely if you have a polarized system. But
right. So you have to have this circulations go opposite. Yeah.
Now, if the amplitude is inverse proportional to K,
Yeah.
what's the energy of the Kelvin wave? So,
Well, we'll come
yeah,
to
because
that.
you see, it looks like the two of them, if you multiply, they cancel each other. So.
Oh no, the energy, the spectrum is K squared, but we'll see that. Okay, the spectrum of
No,
Kelvin
but that
wave.
should depend on the amplitude too, right?
Right. So it's K squared times the amplitude. But
But if you multiply,
Up to an integral.
the amplitude up to the square. That's the problem I have, because I multiply the amplitude squared as usually I do for harmonic oscillator, I think constant.
No, it's not like this. Let's get to that. Maybe it'll become clear, or we can discuss afterwards. But what I want to really focus on is how we can actually describe this systematically and in sort of a no thinking way, right? So Hamiltonian dynamics has been very efficient at that you just need to write down the Hamiltonian and you can use the standard tool to solve it. And in fact, as long as the vortex line, we can single out one vortex line so that this field that I can introduce, field which is basically the x and y coordinates of the crossing of the vortex line with the x and xy plane. Okay, as long as this field is single valued, then I can write down the bias-Samar equation in the Hamiltonian form in terms of this classical field, which is quite importantly is a purely geometrical variable. So actually x and y are the conjugate coordinate and momentum in this Hamiltonian description, and the fact that it's purely geometrical will have quite interesting consequences. Now, if you linearize this Hamiltonian, now this is a standard problem. Then you find the Kelvin waves, right? So that's essentially leaving only the bilinear term in the Hamiltonian, expanding it in small amplitudes. You'll obtain Kelvin waves, and you'll see that those are helical waves, so they sort of wrap around the z-axis, and they actually carry a momentum along the z-axis. This is quite natural, right? They're one-dimensional quasi-particles. But they also carry an angular momentum, which is always -1 for any Kelvin mode, regardless if it's momentum, wavelength, or anything. Any quantum, the quantized formula of the problem carries momentum -1. And this is also understandable because if you look at the cylinder with a straight vortex line, that has the largest angular momentum, and then if you introduce a wiggle, a perturbation, that reduces the angular momentum of overall fluid rotation, and that is essentially what leads to the fact that every Kelvin wave carries a -1 quantum.
Is there an approximation when you write this?
It's the linear approximation. That's the usual thing. So basically,
If the wavelength is very long or something?
right. So the amplitude is much shorter than the wavelength. So the amplitude of your Kelvin wave has to be much shorter than the wavelength. In this approximation, you can expand the Hamiltonian. This is what we're going to do more explicitly, actually, later on. So I'll mention this. But at this point, I just want to say that it's to analyze what happens, how kinetics works out. It's quite tempting actually to use dimensional arguments. And if you do that, then indeed you get the same spectrum as the one with reconnections. the wavelength is the order of the vortex line.
Strikes me here that X and Y are exactly the canonical variables in the old paper by Gonzaga, which I led at this workshop, 1949, I believe, or something. And that's two-dimensional vortices. If you write down the dynamics,
So
so
they could
you're paying that, but actually the Hamiltonian is a log.
Oh,
The
it is very-
separation between it, but
In two dimensions, it would be very different because there's, the main thing that drives the whole thing is
Well, it's not
curvature vortex lines, but there it's different. There it depends on your boundary conditions or whether
yeah,
it's
but take the limit. You see the wavelength goes to infinity, and then probably you'll obtain that.
it's just a
You
straight.
can
Yeah,
change
yeah,
it.
of course.
You should
Yeah,
obtain that.
yeah, but it will be just trivial. It will be just a trivial constant term in this particular formulation. So.
No, you obtain non-trivial dynamics.
No,
in that
wait,
case.
but there the dynamics, the logarithmic interaction of vortices and all that, it all follows from considering many vortices at once. In which
Okay.
case,
Yeah.
and here we're just focusing on the single vortex line. So it's a different problem and there's a different limit, if you will. So there you indeed neglect, all the waves. Effectively, it's a straight vortex, but what's important for dynamics is interactions between different vortices. Yeah. And here we forget about interactions between different vortices. Those are corrections to this dynamics that we're considering now. So it's a self-driven dynamics. Okay? Right. So this dimensional, but the point I want to make is quite important that this actually dimensional argument does not work because all the kinetics depends on the purely geometric dimensionless parameter. If you consider the scale invariant regime, okay, well, the scale invariance naturally leads to the fact that the dynamics must depend on the ratio of the amplitude to the wavelength. So you actually have to solve the kinetic equation to be able to figure out what the spectrum is. And if you do it, I'm just going to flash a numeric simulation as a demonstration. You can start with the k-1 spectrum for the amplitude, and here I also write it for the occupation numbers. For occupation numbers, it corresponds to k-3. You can start with this as the initial condition, but then if you run the simulation, you see that actually the solution transforms to a different exponent, -17/5, which we're going to run in a second, starting from high wave numbers, because this is where kinetics is the fastest, and then it kind of propagates as a wave backwards and becomes increasingly sloped here. So that's essentially already quasi-stationary solution that is plotted here. All right, so the exponent changes, and you have to actually consider it very carefully. But fortunately, well, at least in this parameter, you can see that the spectrum is such, it goes to 0 fast enough so that you have a very well-defined small parameter in the system, the amplitude versus the wavelength, that becomes progressively smaller, and it allows you to build essentially an asymptotically exact theory in this limit. And so with this small parameter, you can expand, and obviously you can just transform this field, this canonical field, to Fourier and introduce quantum mechanical operators formally by the quantization procedure. The problem remains purely classical, so don't be confused by that, but it's convenient to use quantum mechanical terminology, essentially, and formulas like the Fermi-Golden rule, essentially, because it's quite convenient, but you can also solve the problem purely in classical means in terms of waves. Yes?
Here, bk is the height of a small wiggle, or is it the distance from the z-axis?
So I'm looking at a particular, right, it's a height of the wiggle. So I'm looking at a particular scale lambda, and I see how much the wave bends at this scale lambda. Right? So if you expand the Hamiltonian on the small parameter, then you see that the first bilinear term gives you the dispersion, which is quadratic to the logarithmic correction. Okay, and all the high order terms.
K-squared is outside.
Right.
Yeah.
Right. So the k-squared is outside the log. Yeah. And all the high order terms, you can treat them as interaction vertices, essentially. So from naturally, you have a 2-particle scattering vertex, you have a 4-particle scattering vertex, and there's some mathematical expression behind this vertex, which I don't want to bring up at this point.
So in this case, K 3-1 is not related to this local field.
Right. So we have gone away from the local self-processing. So we assume the local self-processing will not happen. In fact, in this regime, they become as when the spectrum changes from K-3 to this 17/5, the amplitude becomes smaller at higher wavelength, and so self-processings become exponentially suppressed. Okay, they become improbable, and you can they disappear completely, and the kinetics is now purely nonlinear, and that's why we have to go to the full Biot-Savart equation, which is written in Hamiltonian terms in this way. Right, so we need to consider the nonlinear interaction between Kelvin waves, and it's quite interesting because most of this problem can be solved purely on considering symmetries, and essentially selection rules and symmetry grounds, except for just one point that you actually need to do computations for.
One question.
Yeah.
You wrote the Hamiltonian, which was pure classical,
Right.
and then you introduced creation.
Oh yes. I should say a couple more words. Right. Obviously, I can do that. You do that with photons, with whatever you want, photons, if you will. But of course, the problem is purely classical. So what I'm going to use, I'm going to benefit from the quantum mechanical formalism, write down the solution in quantum mechanical terms, and then take the limit of classical occupational numbers being much larger than unity in the final answer, going back to classical.
And this just gives you a perturbative way of doing the nonlinear problem.
Right, just basically gives me the diagrammatic theory to work with, which is kind of nice.
You like
The
that?
hope is that you write down kinetic equations in terms of transition rules.
Absolutely. Yeah, exactly. Right, so the symmetries tell me a lot about kinetics. So first of all, because of the rotation around the z-axis that we mentioned already corresponds to the angular momentum conservation, also corresponds to conservation, just standard U1 symmetry corresponds to conservation of the number of kelvins. Okay, so all the scattering between Kelvin waves can be only elastic, you cannot create more Kelvin waves in the scattering, you can only exchange energy and momentum. Now, the translation on the z-axis, is also standard symmetry, gives us momentum conservation on the z-axis, and combined with the fact that we're in actually one dimensions, and that the dispersion relation is essentially k squared, tells us that the first non-trivial, the lowest order non-trivial process that leads to kinetics is 3 Kelvin scattering. Because if you have 2 particles in one dimensions with k squared dispersion, you cannot exchange energy momentum for kinematic reasons. You have to go to 3-particle scattering. So the effective vertex has to be 3-particle scattering. And in the 3-particle scattering, actually, if you look at the Hamiltonian, then the 2-particle scattering with the virtual Kelvin here actually leads to the process of the same order as just the 3-particle scattering vertex. So you actually need to add them up together to get the full effective vertex of Kelvin scattering. Okay, right. So then,
so why is the two Kelvin absent once again?
The two.
What did you derive your thing that is
right. So if you have a k-squared dispersion, you want to solve k1 plus k2 equals k3 plus k4, and k1 squared plus k2 squared equals k3 squared plus k4 squared. Then the only solution of this is k1 equals k3 or 4, and or k4 and k2 equals k4.
So you have only exchange.
K3. So you have no exchange of momentum between the modes. Okay. Or energy, momentum or energy. So it leads it doesn't lead to any non-trivial kinetics. So the 3-particle scattering does. And now we can write down the kinetic equation. So most of this kinetic equation we already figured out. So essentially,
So
there's
the 3-body diagram. You don't have the energy conservation. That's the
the energy is always conserved. No, it's just that.
No, because you see, you destroy the two-body vertex, but you,
Well, I didn't.
that is there,
Uh-huh.
but that it's allowed only because you all have energy conservation, right? So you might have some long-range effects with that diagram, the second diagram. Well, maybe I'll ask you later.
I'm not sure. Yeah, I'm not sure what you mean, but we can discuss that later. Yeah. I must say that the energy is conserved and it's part of the kinetic equation, conservation of energy, conservation of momentum is here. Then the fact that there's three particles colliding leads to this dependence, quite obvious dependence on the occupation number. So basically, the collisional term, so the change, the rate of change of the occupation numbers at the scale K1 depends on the number of particles that goes into state K1 minus the number of particles per unit time that goes out of the state K1. This is what the kinetic equation describes. And this is the only thing you actually need to compute here. This is so all the general structure we've just figured out from purely symmetry considerations. But this vertex you do need to compute. This is effectively this vertex that you need to understand how it depends on K. But once you have this, and you assume, you make a crucial assumption that the collisional term is local in K space. This is quite standard actually in turbulence. It's on one hand, it's a natural assumption. Kolmogorov turbulence. Turbulence also has this assumption. It's exactly the case of Kolmogorov turbulence. It's also necessary to get the Kolmogorov spectrum. Basically, you're saying that in the collision term on the right-hand side, the processes that contribute to the integral are mainly the ones for which all the momenta are of the same order. Okay, this is locality in the K space. If this is true, then you immediately get the spectrum by simple dimensional analysis. This is kind of a standard approach which was used in plasma, but it's a hard lot, where you immediately get, by power counting, you immediately get the solution that corresponds to the constant in the energy space energy flux. Right? And if you want to relate it back to Kelvin wave amplitude, then basically you see that the Kelvin wave amplitude is square root of the occupation number times the K. If you're confused by this, we can discuss this later. It's quite neat, basically just integrating the wave packet around wave numbers over K. And so for the actual geometrical amplitude, this is the spectrum that you get. Now,
you need some form for V also. V1
right, so V, right, exactly. So V, we did compute V here. I just don't want to go into details. You compute V, and actually, this is if you want to do a explicit calculation without this assumption, it is a very tedious problem because you have an order of 1,000 terms on the right hand side because of different combinatorics, and there's many terms that these two vertices they actually translate to a bunch of integrals for this vertex, a bunch of integrals for this vertex, and lots of permutations of those. So there's over 1,000 terms. Oh no, it's purely analytic work. This is purely analytic work. But okay, I'm sorry. Yeah, I didn't appreciate the joke. Sorry, yeah, but it was a good one. Yeah.
So you have probably in the sum over so in the integrals for K2 and K6 only one along the line or
right. So the integrals are one-dimensional on the line exactly.
Why? Why don't you mean you are in 3 + 1D? Why do you only
but because my problem, I reduced my problem by hydrodynamics, reduces my problem to the Biot-Savart equation, which by the fact that the vertex line is not perturbed much, reduces the problem to that of a classical one-dimensional field theory.
So those caverns are all on the same line, which are
exactly. They're all on the same line, which is the first approximation straight, and they're just perturbations on this line which interact.
But you don't have self-crossing.
No self-crossings, no. And this is a very good approximation because they're exponentially suppressed in this regime.
Well, if the amplitude is small, but
yeah, but the probability of scattering is exponential. Here, it's all power laws, where the exponentials cannot compete with power laws of a small parameter. So,
So you get the same solution if you had the Bose enhancement factors in this rate equation, or do you have
These
the
are no,
coordinates actually?
no, this is the classical regime. So I've taken the limit of large n already. So these are,
this is Bose enhancement. This comes from the Bose enhancement. Those and 4 times and
you
5.
can call them Bose enhancement. Yeah. But this is just a classical field, so I have to take a large n limit. But there's no equilibrium. It's a quasi-stationary regime, which is sort of a different. Equilibrium, by the way, it follows from the kinetic equation. You can obviously the detailed, it's a standard thing, right? It's detailed balance in the kinetic equation.
Is there a question, is there an enhancement of scatterings to states that are already occupied?
Sure.
Okay. That's good.
Sure. That's how classical wave physics essentially works, right? So you have to have these stimulated processes are much stronger than the what's the other one? Spontaneous. Thank you. Right, spontaneous are obviously neglected in this limit. Right, but we were actually challenged in this locality assumption, even though we checked it numerically, that wasn't nice enough. And we were challenged by Wolf and Nazarenko and their students who actually computed all the 1,000 terms, and they actually very proudly did that. And we probably wouldn't be able to repeat this calculation, but they say based on direct calculation, you see that the collisional term is actually the local. Okay. So that was a bit of a fuss, and the because everything is essentially power law, the collisional integral converges in one limit. It converges automatically because of the powers at large momenta, but actually at small momenta, the convergence of the integral can only be ensured by exact cancellation of all the 2,000 whatever 1,000 terms that you have, right? And they just did that explicitly and said no, it doesn't cancel. Right, so the solution has to be changed, and they came up with another solution. However, it turns out we can actually figure out that the collisional term is local from purely symmetry grounds, and it's just the proof goes like this. I can assume that the collisional integral is non-local for this particular spectrum. Then, if I'm considering collisions in short length scales, is K1, then the contributions from small length scales, so non-local, again, I need to remind you, non-local means that there's a direct energy transfer from really long wavelength, the longest actual wavelength, because of the divergence of the integral at small momenta. The longest wavelength talk directly to the short wavelength and modify the kinetics of the short wavelength. So in the collisional term, I need to consider the kinetics of those short waves on top of long wavelength structure, which I can actually parameterize because these collisions, they happen locally at the length scale of order of the wavelength. I can parameterize by local geometrical characteristics of long-range geometrical characteristics of the vortex line, such as, for instance, the amplitude, the angle, the curvature, and I can keep adding terms if I need to. However, I see that from the symmetry considerations, I can rule out most of them. The transverse translational symmetry, so we haven't used the remaining 4 symmetries, but if we can use them, we see that the transverse translation means that the dynamics cannot depend on the overall amplitude of the system quite clearly. So the overall amplitude of long wavelength modes drops out of the problem. The angle must drop out due to the tilt symmetry, because obviously I can tilt the line and the physics will not change, right? And therefore the kinetics at short wavelengths can only depend on long wavelength curvature of the system. Okay, but if this is the case, then I can look at I can write down the collisional term in terms of the large scale curvature, and then for this particular spectrum, I find that the curvature, which is an integral like this, actually builds up at the upper limit, not the lower limit. So for this spectrum, the curvature builds up at the main contribution to curvature comes from short wavelength, not the long wavelength, right? And therefore, this K that enters the collisional term is actually depends only on the same scale K, and therefore the collisional term is local.
It doesn't mean EOP.
Huh?
EOP doesn't-
Yeah, I wrote it 10 years ago. I think I meant end of proof. I must have seen that somewhere. That was a punchline when I wanted to make a lot of noise out of it. But, yeah. Right, but yeah, but the point is that not everybody buys it, and unfortunately, but it's a very simple test. I just want to advertise a test. A very simple test that nobody has done in 10 years somehow. It's
conclusion is EOP not equal to EOD.
right. Well, it is. It is. If you're a theorist, it is. But if you trust in computing 1,000 terms and adding them up to 0, then it's a different story. Well, I would go selection rules over direct calculations. But in any case, there's a simple test that nobody has done, unfortunately. But I've been offering it as a master's student project. Well, students are a bit intimidated by superfluid turbulence, but eventually somebody should do it. So if you start just with a ring, which is a nice, easy problem, and create a small wiggle on the ring, then the local and non-local scenario will result in a dramatically different scale of the kinetic times. So essentially, you can measure, you can observe the times. You can even do it in quadratic experiment if you want. You can observe the time it takes for the amplitude to decay by, I don't know, factor E or 2, and that defines the kinetic time, and you see that the time scales with the amplitude in local and non-local scenario quite dramatically different. Okay, they're different.
Is that ring two-dimensional or three-dimensional?
It is everything has to be three-dimensional, so it's a three-dimensional volume, and the ring is just the simplest sort of, because you have your favorite very boundary conditions, and it's very easy to implement in your, I don't know. We have wonderful simulators in the helium community, but somehow people stay away from it. Maybe I should not be saying that for the camera, but I mean, maybe for political reasons. But I would like to encourage somebody to actually do this problem and settle this so that everybody's. Yeah. Right. No, but I need to say the encouragement on the camera. So.
Yes.
Right. So okay. So there's a lot of things that I wanted to mention, but obviously I'm out of time. There's quasi-classical turbulence and all this that is involved. I just want to say a couple of minutes. I want to talk about the radiation of sound, because for theorists it's a very beautiful problem. In fact, it contains a lot of ingredients that I think make it very, very beautiful. So there's a few control parameters which allow you to build a controlled Hamiltonian description of interaction of vortices with phonons. Well, one of them we're familiar with is in hydrodynamics. That is, the vortex core radius is much larger than all the other length scales. Then the fact that the Kelvin, as long as the Kelvin waves amplitudes are small compared to the wavelength, that gives you another small parameter. And we've already used this in Kelvin wave theory, and indeed at those wavelengths where the radiation of sound is important, this small parameter is there. And also, we can introduce phonons if you assume small density fluctuation, which is also for phonons. But most importantly, the fact that the wavelength, the typical wavelength, are much longer than the healing length, the vortex core size, means that the dynamics of vortices is much slower than the speed of sound, essentially, if you translate that into velocities. And that means that the coupling of kelvins to phonons is non-relativistic. So it gives a very good small parameter. This is a very small number. Very small, good small parameter to build a perturbation theory. Okay, and expansion. But the perturbation theory has an interesting twist to it. So if you consider, you need to find what the variables are, vortices and phonons. And if you do the standard decomposition of the phase fields, obviously the velocity is given by the gradient of phase, and you can decompose the phase into a singular contribution that comes from vortices, okay, which has non-zero circulation of velocity, and a regular part that corresponds to the harmonic modes, and you could call them phonos. Okay. So far, this decomposition is not unique. I mean, clearly, I can add any part of a regular part to the singular part, and this doesn't change my
Can I
definition.
say that you take the velocity field, decomposing potential and rotational? Is it the same thing?
Harmonic and topological or singular, depending on which term it
The
depends.
first one is rotational, the second one is potential.
Well, it's irrotational in the sense that the curl is zero, so it's irrotational, but it has a topological defect with,
No, I say
with
it's
non-zero
rotational. You see, so-
circulation. Huh?
So there you have a curve different from zero.
No, curl is zero because the velocity is gradient. It's
No,
non-zero
but you have
only.
a singularity of zero, so it's not zero.
That's why we can call it topological.
Yeah,
or-
but whatever,
Yeah.
that's terminology.
right. So,
It's like you have a Dirac string than the rest, you see. That's. I wouldn't call it-
Okay. well, okay, all right. So the standard decomposition that makes it unique is the requirement that the Laplacian of the singular part is zero, which actually corresponds to the incompressible fluid approximation for vortices, which we touched upon, and in particular, it tells us that the energy decouples from well, if you remember how, for instance, the Kostelis-Thales theory works, this is exactly what you do there, and there it allows you to decouple vortices from phonons and make the calculation seemingly natural. But you can, if you think about it, this decomposition is actually deeply unphysical, okay? Because the solution of the Laplace equation is unambiguously determined by the position of the topological defects. Right? Once you fix the defects, you solve the Laplace equation, and it defines the field phi zero everywhere in the fluid. Okay? But obviously, if your vortex moves, then the field at large distances cannot instantaneously change if you allow for the presence of phonons. And therefore, actually this long wavelength parts of the field should actually belong to phonons, not vortices. Okay, so you can actually see that this decomposition in the presence of phonons, when the phonons are relevant, this decomposition cannot be physically meaningful as into vortices and phonons. And well, just a couple more slides left. If you're unsure about what the canonical variables are at the Hamiltonian level, obviously the way to go is the Lagrangian, where it doesn't really matter what variables, whether they're canonical or not. And there you can actually figure out where the variables are. So if you start with Lagrangian for vortices, then you have the standard density times phase dot term that defines your canonical vortex variables, and Kelvin-Dave Hamiltonian. If you work it out, you will get your quantized operators that we had in the Kelvin-Dave problem. Exactly the same Hamiltonian as well. This is quite nice. Then if we consider phonons separately, the problem is quite similar. We can also quantize this density and phase, our canonical conjugate variables. We can quantize the problem and introduce phonon modes. But if both of them are present, not only do you have an interaction term in the Hamiltonian in the energy, it's not Hamiltonian yet, in the energy, but you also have a term with a time derivative that actually couples the variables. So you can actually see that the variables are not canonical in this formulation. Okay, but with the help of this small parameter, this k times a0, the non-relativistic parameter, you can actually eliminate this term systematically. You can expand this term with respect to the small parameter and transform the variables, perform a variable transformation by eliminating this term, and arrive at the canonical variables of this problem. And that gives you actually quite an untrivial structure of the Hamiltonian. So if I start with the Hamiltonian in terms of the original variables, and we write the original variables in terms of the actual canonical variables, I generate a whole set of vertices which are responsible for the conversion of Kelvins into phonons.
Okay, so the straight line lines of Kelvins, straight lines of phonons, and the interaction term actually was considered before, some 50 years ago, but better, and it stays the same essentially in this approximation. It's not changed. It's mainly responsible for scattering. Okay, so then of course the radiation of sound is actually driven by, once you have this Hamiltonian, you can write down the radiation of sound, and the vertex that is responsible for this is the annihilation of two kelvins. You need 2 kelvins because of the huge mismatch between momenta, as usual, right? So unless you allow Cherenkov radiation, the phonons go fast enough. You need 2 of them, and because each of them carries a angular momentum quantum -1, the phonon that you get has angular momentum -2, so quadrupole radiation. So I can compute the power of quadrupole radiation, but basically this formula, the constant is the only thing that you need from this vertex, right? The whole thing, this you can find in Landau Lipschitz, as long as you know that it's a quadrupole radiation. It's the same classical physics formula for sun radiation, right? Quadrupole radiation. And so you can estimate where the cascade is cut off, and it's cut off at around, well, for typical experimental parameters, of course, it depends on the experiment, but typically it's cut off at micrometer scales, which is still much longer than the healing lengths, so you're well in the hydrodynamic description. The description is valid. And my final slide, I just want to make a point that this Hamiltonian theory has allowed us to get insight into some of the long-standing debates on vortex scattering. In particular, there was a problem of elastic scattering, which was solved many times. It was solved first by Yardansky with some errors in numbers. Sonin fixed them up. I mean, ASK, I think, also. There were some factors of 2, Sonin fixed it all. But then there was a series of work studying with Fetter, who considered the Hamiltonian approach and derived a different scattering cross-section. And there was a debate which one is correct. And it turns out that if you include the terms that come from the variable transformation, when you transform the problem to the canonical variable, you recover the diagram, which has the meaning of a virtual displacement of a vortex during the scattering process. And this diagram actually accounts for the difference between these 2 answers. You recover the correct answer, and actually it was already argued by Sonia, I think, that the answer by Fetter corresponds to the P vortex, and then you see how, from the Hamiltonian formulas, we actually recover the correct one, because these vertex, which comes solely from the transformation of variables, accounts for the virtual displacement of the vortex during the scattering. It's equal. Right, so in scattering theory, that will be equal. Right, in diagrammatics, it's just virtual Kelvin that you have there. Right, and similarly, if elastic scattering has not been discussed that much, except by Fetter, but it needs to be corrected by a similar vertex. Okay, so I should end here. We're well over time, and I'll just leave my conclusions. Thanks a lot for your attention.
So one problem that can arise when you write the kinetic theory is that you need a small parameter so that like 5 body collision is weaker than 3 body collisions, for example. Right. Now in quantum mechanics, it's okay because your occupations are small, so occupation number times the.
It's not this. It's the kinetic times that is important. It's not the occupation numbers that controls the theory. In fact, what controls the theory is the typical times time scale determined by the collision term.
Sure.
So you can use the so-called random phase approximation in the classical field theory, where the the phase rotation due to the energy essentially is much faster than the change of occupation modes
due to collision. Yeah, that's right. So scattering length or scattering interaction strength times the occupation numbers could be a good quick estimate of that hierarchy.
In some powers, yeah. So the scattering vertex times some power of k due to conservation laws times the occupation numbers to power 5 give you the estimate of the original time.
So now my question is that since you are in the classical regime where your occupations are quite high, do you still maintain this hierarchy? Or can you?
Yeah, the
argue?
answer is yes. I'm not sure I understand what confuses you, so but the correct answer is yes.
Okay.
Oh, so you saw some nice how it came on.
Right.
Okay. And I'm wondering how it looks when you plot vortex length as a function of k.
Oh, that's a very good question, actually. That is a very good question because the vortex length is here is it grows very quickly because it's essentially fractalized regime, right? So you have a fractal. Your length is of order of your amplitude is order of the wavelength, and I mean I have a plot somewhere. I can show you later. I can maybe show now. We don't have much time. I can just flash it for you if you want. We actually compare it to the experiment, because an experiment you don't have explicitly, you don't have direct access to Kelvin wave amplitudes. You have access to the length. And you can actually measure the how the length changes. So essentially, this is the essentially theoretical fit of the theory to the vortex line length versus the mutual friction coefficient, which you can think of as temperature. So if the temperature goes down, that is the somehow I'm not. Yes, this plus. So anyway, so effectively, this is temperature and going down that way. So as temperature goes down, the line length increases because you have more and more length scales entering the system, and the vortex line becomes essentially fractalized and in a wider and wider range of scales. And this regime essentially is the regime of self-crossings is the one that is responsible for the biggest growth of the line length in the system. So if you integrate, obviously you just need to do this integral, and you'll observe that gives you the biggest line length growth.
So apart from the mathematical rigor, k to the minus 1, k to the minus 6 over 5 is a really small effect.
It is a small effect.
I mean, is that something that can never actually be seen in experiment? I mean, I have no idea
Well,
what error bars would be.
Well, you can see it in numeric simulations. Clearly, if you can do a cold atom experiment with a Feshbach resonance, we have a good separation of system size and healing length, maybe extra factor of 10 and what is now, so that you have at least a decade in the K space, you can resolve them. So if you have a decade of wavelength scales in your spectrum, then you can resolve the difference. But of course the question is not the main. It's quite customary in the community to reduce debates about mechanisms to the debates about the spectra that result from those mechanisms. So the spectra, the fact that they're closed, it's natural because it's dynamics and physical, overall physical nature is the same. But the main question is what is the actual mechanism that drives, and then of course the spectrum is just one manifestation. But as I demonstrated, for instance, in the non-local versus local kinetic theory, you see that if you look at a different observable, you see a drastic effect rather than just a small change in the spectrum.
So as the amplitude of photons or whatever gets larger, you've talked about when it gets big enough, you start to get self-reflection.
Right.
Is there anything else what else is known about what happens as the amplitude gets larger?
There's not much more in the problem because in those length scales there's no phonons. You can neglect all the microscopic details. So it's pure high dynamics with geometrical vortex lines. So the only thing you can have is essentially just the separate connections between them. I can't think of anything. They could be exotic, like in this example, for instance, there could be some exotic effects in some particular special cases that you can come up with, but generally that's about it.
I guess I'm asking because it seems like there's a gap between assuming that the amplitudes are small compared to the wavelength.
Oh, no, it happens continuously. No, it happens continuously because as the amplitude slowly goes down, so the amplitude is a order of the wavelength in that self-reconnection driven regime up to logarithmic correction. So this logarithmic correction eventually, in the theoretical limit at least, large K, it will reduce the amplitude so that the reconnections become rare. They still happen, but very rarely. But as soon as they're rare, then you can see that the purely nonlinear collisions between the waves start carrying all the energy. And that further suppresses the amplitude and completely suppresses the reconnections. So it's a continuous transformation, but you clearly understand how this happens.
I have one question, two questions. How does polarization change the picture?
Right, so I skipped the whole section of the talk because I wasn't expecting that many questions. I thought we were well trained by No, I'm kidding. So the polarization changes the picture at large scales a lot, because in fact we can actually demonstrate that superfluid turbulence at large scale, the scale is much larger than the typical separation between vortex lines, as long as you generate it with steering or some kind of classical means so that it creates a long range of long distance vorticity, is equivalent to classical turbulence, described by the same equation of motion, same vorticity equation. So in this sense, at large scale, it must be a coupled motion of vortices that mimic classical eddies that drives the cascade, and there's nonlinear Kolmogorov physics all over the place. But then eventually, as you go down to shorter length scales, then the self-driven dynamics of vortices, that is dynamics that is due to curvature and essentially local induction approximation, starts becoming important over the coupling between vortices. And this logarithm 10 essentially tells you when it happens. So this big logarithm is a prefactor in front of the self-driven dynamics compared to the interaction between vortices-driven dynamics. So you see that when there's fewer than about 10 vortices in your bunch, then they start behaving independently from each other. And this is where you need to consider the locally induced motion more specifically, and then you end up with all sorts of reconnections that you can have, and a gradual transformation of the cascade down to the individual vortex line where you have Kelvin waves and all that. I had a few slides on this, but we can maybe discuss it later.
Anything else? All right. Thank you very much.